Okay, so in the previous segments, we were looking at some of the important functions of operating systems, and we came across the term process in multiple contexts. So we looked at process scheduling, we looked at something called resource allocation for different processes. So we saw that there are certain functions an operating system performs which have got something to do with this term called process. We came up with a loose definition of the term process, which we understood is any task or any function which the computer is performing. So in this segment and the next few segments, we will be taking a closer look at processes, what they are, what they're made up of, what happens when a computer is trying to execute a process, and some of the technicalities related to that. So we'll start by looking at the definition of a process and some inherent properties that every process has, such as the memory space allocated to it, the different states it can be in, the process control block, and so on. Then we'll look at threads, which are again a subdivision of processes. We'll take a slightly more closer look at scheduling of processes. We'll see an important topic called context switch, which happens in multitasking and multiprogramming when we move from one process to another. We will briefly touch upon the operations that can be performed on processes, and then we'll be spending some time looking at IPC, which is inter-process communication, one of the important functions of an operating system. So these are some of the broad topics we're going to be covering in the next few segments. Right, so we will begin by defining a process. What is a process? So the Silberschatz's and Galvin textbook for operating systems defines a process as the unit of work in a modern computing system. So a unit, as we all know, is the standardized quantity using which as a reference we measure anything. So you have the unit of distance is meters, unit of energy is joules, and so on. Whenever you're measuring a quantity, you measure it using this unit as a reference. So when we say a process is a unit of work in a computer, it means all the tasks which are being performed by the computer are measured in terms of a reference standard called processes. So to put it in simpler terms, every activity or every task or every individual function which a computing system performs is taken as a separate process. So every process has its own memory address range and cannot access any location outside of this range. So a process, as we just saw, is basically one task, right? So if you're using a computer and let's say you're listening to music on one tab, on another tab you have, for example, PowerPoint open and you're typing some content, you're creating a presentation. On another tab of your browser, you have some images open, so you're copy pasting the images from the browser into PowerPoint. So right now there are three different applications running in your system. There's a music application, there is PowerPoint, and there's the browser. So, and you will probably visit another URL, Wikipedia or something, to look up some facts as you're typing into the presentation. Once you're done with your presentation, you'll open your notepad and you'll make a note in your to-do list that this task is done. So each one of those tasks is a separate process. So one task qualifies as one process or job. So let me note here that task, process, and job, for the purposes of this course and these lectures, are interchangeable terms. So when I say job or task or process, I am referring to the same thing, which is one activity or one function to be performed. So each of these functions, as you can see from the example I gave you, might be totally independent of each other. You might be using two or more of them parallelly at the same time, and each of them is going to be doing a different task or working with a different set of resources and different chunks of data. So each process has its own memory address range. What do we mean by this? So you know the computer memory is identified by memory addresses or memory locations, right? And we know that these locations are contiguous. There is an ordering 1001, 1002, whatever. We like to give them numbers. And there is a range. So if your computer memory is so many GB of RAM, then it means there are so many unique address locations. So starting from this and going on up to this. So So that entire memory, of course, is going to be divided into segments, and certain segments are going to be allocated for certain processes. So for example, if the data pertaining to a specific, let's say you have some photographs stored in your D drive, for example, and if you want to copy paste those photographs into your PowerPoint presentation, you will access the data which is stored in the memory locations corresponding to that D drive or whatever folder. So every process has specific things which it is going to do, for which it requires specific units of data from your computer memory. So it will be allowed to access specific locations of the memory, and the process cannot access any location outside of this range. So if you remember this from the previous segment, from one of the things we looked at yesterday, no process should be allowed unlimited access to the CPU's time or resources. And when we were discussing this point, one of the things we mentioned was, if any process gets such unrestricted privileges, it might go and alter the OS itself, or it might go and tamper with some critical information and render your whole system useless, or it is a potential threat, right? So that's the same idea we are carrying forward here. Every process has some data which it is allowed to access, which it will be required to access, and it should be given access to the memory locations containing that data and not to any other memory location outside of this range. So let's say you have two processes, P1 and P2, and let's say P1 requires data which lies in the range 1001 to 1010 on your computer. Let's say P2 requires data which ranges from 1021 to 1030. Then throughout the course of its execution, P1 will only allow to be accessed the memory addresses from 1001 up to 1010. If P1 tries to access the location 1025, for example, it will be blocked. The OS is supposed to tell the process, you are trying to access a location which you do not have a right to access. So access must be denied, and P1 must be redirected to whatever it was doing. So that is what we mean by the third point on the slide. Each process has its own memory address range, the range of addresses which it is allowed to access, and it cannot access any location outside of this range. Alright, so now that we are already talking about process memory, we will also look at take a closer look at the memory pertaining to each process. So like I just mentioned, every process has a bunch of addresses allocated to it. Outside of these addresses, the process is not entitled to access any other location, but within these allowed memory addresses, what do we have? So these allowed memory addresses are generally divided into 4 segments: text, data, heap and stack. So if you look at it, this entire big rectangle here pertains to the memory which has been allocated for one process. So it starts, let us say, from 0 and goes on up to some address which we notify here as max. Now this entire rectangle represents the memory space allocated to one process P1. This is divided into text, data, heap and stack. So these are 4 separate types of memory, and each is going to store a separate type of data, each is going to do a separate task. So the text part is responsible for storing the code and instructions pertaining to that process, the actual process, what the process is supposed to be doing. The data part is responsible for storing the value of variables and so on. So again, going back to your computer organization, let me recall your attention to the point that there is a difference between data and instructions. So data is just the variables, the operands, the numbers, so to speak, on which you perform an operation. Instruction is everything together. If you say add x comma y, then x and y are the data, but the add part along with x and y, everything together forms the instruction. So taking that analogy forward, text part here contains your entire code or entire instruction. Data part will only store the values of the variables. Heap is a dynamically growing memory which is allocated during runtime. So when your process is being executed, if some new variables are being created or some necessity for extra memory comes up during runtime, it will be stored in the heap segment, and as soon as that runtime, that execution completes, this will be erased. and stack is mostly for recursive function calls and that kind of thing. So if you know, in recursion, when a function calls the same function, a stack is created, and the function calls keep accumulating. Once the base case is reached, the stack is unwound, and that is how we keep going back. So that thing happens using stack. So and that new function call that gets pushed into the stack is called an activation record, which is just a technical term. So the key takeaway I want you to have from this slide is every individual task that a computer performs is called a process. Every process has a range of memory addresses which it is allowed to access. Outside of those addresses, it should not be provided access to any other memory location. Within those allowed addresses, we have 4 subsegments: text, which stores the code and instructions; data, which stores the values of the variables; heap, which is dynamic memory allocated during runtime for anything which you might want to store while the process is being executed, and the heap gets deleted or destroyed as soon as execution is complete. Stack again is also dynamic. If you can look at the diagram, you'll see that for heap and stack there are arrow marks which denote that the size is dynamically growing. And this is for recursive function calls and mostly anything that's of a meta nature.